And now we're going to focus on the bias terms right here, which is also what we're going to do right here. The first line we have to calculate is this one. So I'm going to print the values that we have first. Remember that our convolution doesn't have a bias term that is set to none. Convolution weights have a shape of 64 by 3 by 6 by 6. So here we're saying if conv.bias is none, which in our case it is, then this is the value that I want you to return and assign to bconv. Now conv.weight, that size, is 64 by 3 by 6 by 6. Another way of doing it would have been to call conv.weight.shape, same results. You can call the property shape or the method size, and you'll obtain the same result. And then here, we could have just called the first index and return 64. But in this case, within the size method, we're asking for the value of index 0, which is 64. We're specifying the dimension that we want to return. So if we don't provide any dimensions, then we get the shape. If we provide the dimension, then we get that dimension as output, which in our case is 64. And because we're calling it within the torch.zeros, we're saying, give me a vector of 64 zeros. And that is what we're outputting right here. So we can just run this. We can also run it here. And then bconv, a vector of 64 zeros. Now we're going to focus on this line of code. So let's print those variables first. Now here, we're calculating the batch norm bias, which we can also see it right here on the right, essentially these, which are the bias parameters minus the weight parameters times the mean divided by the square root of the variance plus the epsilon term. The bias term minus the weights, and that is multiplied by the running mean divided by the square root of the running variance plus epsilon. So I've printed those values here. We're just using the parameters that were learned during training of the neural network. These values are the mean and the variance of the input images that were used during training. So these are the values here. Again, 64, because it's calculated for every output channel. So we run that. And also we can run it here. So batch norm, these are the values of the batch norm bias, negative 0.58 and 1.40. Batch norm, negative 0.58, 1.40. And right now we're here. Let's unpack it a little bit. So let me run this first. So here we want to do matrix multiplication of the batch norm weights and the convolutional bias. And then we're going to reshape it. And then we're going to add the batch norm bias values here. Is this right here. The weights of the batch norm, that product with the bias of the convolution, and then summing that to the bias of the batch norm. So the batch norm weights are 64 by 64. Again, the diagonal that we calculated earlier. See that the weights of the batch norm were calculated right here above. And then the bias of the convolution, well, we already obtained that. And the bias of the batch norm, we calculated that in our previous step. So here, matrix multiplication between 64 by 64 and the convolutional bias terms, which in our case are 0, but they could have value if they were defined in the architecture. Now, this originally has a shape of 64. It's just a vector. And then here we're reshaping it. Our dimensions are 64. So it's a 64 by 1. So it's a two-dimensional tensor. So the 64 by 64, WBN gets matrix multiplied between that and bconv after it has been reshaped. So the output would be 64 by 1. And then 64 by 1 will be reshaped as well, removing the extra index. So it will become, after this reshaping again, a torch size of 64. So the 64 becomes 64 by 1 so that the matrix multiplication can be performed. And then the output of that gets reshaped to 64 only. And then that plus BBN is the result of this operation. So BBN, as you can see, is 64. So same dimensions, and the result is calculated here. So the bias of fused conv has been updated with the matrix multiplication of the weights of the batch norm and the bias of the convolution, reshape. And then that has been reshaped and then summed to the bias of the batch norm. And the result is stored right here. We obtain negative 0.58 and 1.40. when we run this fuse conv bias, negative 0.58, 1.4, as you can see, the output of this is just the batch norm bias because these values are 0, given that bconv is 0. Okay, so let's recap. So we've calculated the new weights by performing the dot product between the weights of the batch norm and the weights of the convolution. The weights of the convolution and then the weights of the batch norm, which we create a diagonal matrix of these values right here, which are these values right here. Essentially, we created this matrix and we performed that product with the weights of the convolution. So essentially, we performed this operation. And then we calculated the new bias term, essentially the weights of the batch norm layer, that product with the bias of the convolution, which is 0. So this term is 0, plus the bias of the batch norm. So essentially, our new weights are these, and our bias is the result of this. Now, the output of fuse conv and batch norm is m.conv. Remember that fuse conv is a convolutional layer that now has the combined values for the weights and the bias, but is nevertheless a convolution. Now, the output of fuse conv and batch norm will override the current values of m.conv. Remember, m.conv had bias to none and had these weights. When we run this, m.conv now has the bias and the weights result from this function right here. Now we've updated the m.conv, but m was iterated right here, and m still has the batch norm term right here. But given that that is already implicitly inside conv, merge, and fused, we want to delete m.bn, which is what this is doing right here. So m.bn just got deleted. And then here, now we're going to override the m.forward method with m.forward fuse. So let me show you what that is first in the Colab environment. So our fused conv, which has the values for the weight and the bias, we're gonna save that into m.conv. But remember, so what we want to do is delete that value so that we only have the conv and the activation function. And then here in common, before we were doing the convolution and feeding that to the batch norm and then feeding that to the activation function. But given that we have combined these two, we don't want to run the forward as is. We want the forward to run the convolution, which the batch norm already integrated in it, and the activation. So essentially, when we do the forward pass of the image to the neural network, we don't want to run this, we want to run this. And this is what this is actually doing. The forward fuse method is what we want to run when we perform the forward pass. When we have the input image, the conv class will call the forward method, but the forward method would have been overwritten to perform this operation. Let me show you. So m.forward fuse will call models.common.conv class, and then the forward fuse. If we do m.forward, we will perform the forward method. If we override it, when we call the forward method, we will actually be calling the forward fuse method. Another way of seeing this is here. M, function variables, forward is right here, and forward fuse is right here. When I run this, our forward fuse has been saved in forward. So when we call the forward method, we're actually calling the forward fuse, as you can see here. Now we just perform the fuse of the convolution and the batch norm for this one layer, but we have 101 layers in this neural net. So we are going to perform these operations in the 101 conv classes. And then after that, after we've performed and iterated, we will print the parameters to the terminal.